So now digging deeper, how does this all work, right? When we say, virtualization at user space, exactly where is it? How does it actually work? So here's a basic stack. You have the application over operating system, you have hypervisor, and then you have your physical resources. And so what we do is we've introduced a layer between the application and the operating system, where this is actually running in the context of the application, virtualization capabilities, right? So we have abstraction layers, like device abstraction, memory abstraction. Then on top of that, we introduce features, things like pooling, things like scheduling, and caching. And so if we go deeper, what does this actually look like? Has anyone used CUDA before? No? Okay. This is how new it is, right? This is just, people are just starting to use, CUDA, GPUs, AI/ML, but it's very, very fast growing. So let me just kind of explain how a typical application works in the AI/ML space. So you'll have an application. So let's say it's doing, it's driving a car, or it's, doing object recognition or something, right? It's going to use a set of libraries, and these libraries are provided by the hardware vendor. And these libraries are basically for hardware acceleration, right? So instead of using a math library that's generic, you could use a math library that's specific to this vendor that takes advantage of that hardware much better, right? And just like many I/O devices, you have two kinds of drivers. You have the user space driver, and then you have the kernel space driver, right? And the user space driver and kernel space driver are the two things that talk to each other, right? You see this in pretty much every I/O device out there, right? A user space component and a kernel space component. So the same model exists here. So you have a user space driver and a GPU driver, and of course that GPU driver will be in the context of the operating system. It'll be on a hypervisor, and then it would have access to those devices. So now when we talk about the sweet spot, this is the sweet spot. So we're above the user space driver, and we're under these libraries. So if we go too high, then we're application specific. If we're too low, then we have then we have a performance problem. This is sort of the sweet spot. This is where we introduce virtualization. So how does this look like? So we're going from this view, and we're separating this into two different pictures. You have a client portion, which has the application and a bunch of libraries, and you have sort of the server part that has the actual hardware resource and its associated drivers from the vendor. And this is what it would look like. So the server part, right, the CUDA driver, this is the user space driver, and it would have the kernel mode driver in here in the context of the application on this side. And on the left side, you have the application, the associated libraries, and then we actually interject ourselves, this virtualization in the middle of that. So the application runs, we actually intercept CUDA or OpenCL or whatever the compute API is. We apply our virtualization to it. Examples are typically the first thing you do when you're querying, when you're using these coprocessors is simply to figure out how many are there, how many devices are there, right? And so we can say that normally in the system you would have no such devices. We can actually say, well, there's actually 3 over here, or there's 2 over here, right? So we can manipulate the return of these APIs. We can change how much memory is reported, et cetera. And so the virtualization component really starts at the client. Those API calls are then routed over the network. It's received by the Bitfusion component on the server side, and the server side would then relay it to the vendor driver, right? So this is a dramatic oversimplification of what actually happens. You can imagine that this feels slow. You're going through a lot of layers, right, of the stack. This is one at a time. And in fact, there's a lot of performance optimizations. There's a lot of changing from a kind of synchronous API stream to a much more dynamic graph-based stream, really taking advantage of pipelining, really trying to overcome the latency of networking, et cetera. So there's a lot of complexity here. But this gives you kind of a very basic overview of how things would work.
Yeah, like you said, this is a generic representation. I mean,
Yeah.
referring to the network just as network, but can you talk a bit about what the actual underlying fabric is required to enable dynamic remote attachment of these high bandwidth devices?
Yeah. So when you first start, there's actually a negotiation between the client and the server, right?
But like what physical fabric
Yeah.
technology are you using to enable this?
So we use normal, just standard networking. So it could be over Ethernet, so TCP/IP over Ethernet. It could be, RoCE over Ethernet, so RDMA over Ethernet. It could be InfiniBand. So these are the three network transports that we support. And of course, in the VMware context, there's VMXNet3, there's PVRDMA. We take advantage of those two as well.
Are there any special considerations for the network architecture? Are we setting up a dedicated network to enable this, aside from the normal virtual machine networking?
No. Now, what you typically want to do is, so we have some guidelines. So basically, how much compute you'd want to attach to a client. If you have, kind of the latest generation GPUs and you have 10 of them, it doesn't make sense to use all 10 at the same time over 1 gig Ethernet. There's a massive imbalance. So we do have some guidelines. Typically, 10 gig Ethernet, normal data center, you'll have overheads of 10% or less. Right? There are some tunables within VMware that we do recommend kind of to optimize the link latency as much as possible. But in general, this is really designed. We spent a lot of time just making it work really well in just common commodity data centers. Right? You don't need RDMA necessarily, even though it would help. You don't need any exotic hardware to make this work well.
So, of course, this will drive up the utilization of the GPU, the remote GPU. But actually, the server that hosts the GPU, okay, because of the bandwidth that the GPU can create, will be killed for any other kind of workload. So if I have 10 servers accessing a GPU, and this GPU generates, 10 gigabytes per second.
Yeah.
So it's a massive amount of data that transits all on a single.
So that's actually what we thought when we first started developing this. So it turns out that it's not as much a bandwidth problem as it is a latency problem. So if it was a bandwidth problem, we've run into a physics problem, right? Because you can't introduce compression. That's just one word. But it actually happens to be latency. So there's a lot of interaction between the application and the GPU. And so a lot of what we've done is to optimize the stream to make it as latency insensitive as possible. But if you were to look at bandwidth, yes, it bursts at 100% for short periods of time. But if you look at averages, you're even at 10 gig, you're actually using a fraction of it, which is surprising and not conventional wisdom. But yeah, good question. Okay, so this is how it works. Again, there's a lot of things that to make this actually practical. To make it optimal and validated has taken a lot of time. But all of these techniques are actually generalizable to other architectures as well. So this is implemented in such a way that we can introduce other accelerators very quickly and take advantage of all these performance optimizations. So it's actually practical over a commodity sort of data center.
And so CUDA is a standard now. There is no standard for FPGAs at the moment, so they are all different. But actually, for example, IBM is working on a family of then more or less some of them have this similar APIs. Do you think that in the future you will be able to implement something similar for?
Yeah. So we actually support OpenCL. So for the early history of Bitfusion, we had thought that the industry would move towards CUDA, which is the dominant proprietary API, and then a dominant open source API, OpenCL, which has its own standards body, Cronus group. That actually didn't happen. What actually happened is everyone is going proprietary. So the FPGA vendors are going to have for Xilinx, this XDNN, they'll have a deep learning neural network library that uses their coprocessor, and they'll integrate that into TensorFlow. Other AI ASICs are doing something similar. They're creating their own libraries, acceleration libraries, and then integrating that into TensorFlow. So that's what the industry has been, kind of going into. And so when we talked about where in the stack we are, in the sort of sweet spot, one of the bullets, if you look back, is that we have to develop a set of tools that makes it easy to take proprietary implemented acceleration libraries and plug that into this technology. So we spent a lot of time making the tool chain in such a way that it's very easily pluggable. But that, I think, is that is essentially what's happening today, whether it's from Intel or any of the FPGA vendors or even the DSP vendors, AI ASICs, it's all proprietary libraries. Nothing is standard yet.
Yeah. Well, this is probably because it's about, they are building platform and they want to win on the features that they have on their platform, so they don't want to share too much. Yeah, and
I think architecturally there is always this trade-off between generality and efficiency, and I think in OpenCL, everyone's experience has been that, well, OpenCL is so general that it really can't, really access the performance of this accelerator. There's too many layers of abstraction, right? Defining a buffer, well, I could have 10 kinds of buffers, right? How do I really use all these extensions? So I think the world right now is keep it simple. An AI ASIC would introduce a library, spend 2 weeks integrating that into TensorFlow and then shipping, instead of spending years with a standards body and trying to
good at everything, but not very good at anything.
If you look at kind of the history of computing, I'm sure the pendulum is going to swing. People are going to come up with, okay, guys, there's 1,000 accelerators. Let's try to come up with an acceleration library that's general, that everyone can be happy with. That's sort of how history repeats itself, right? I want you to give a little bit of favor of where we think accelerators are going, right? So accelerators, if you think about kind of a common system, you have a host, we have a bunch of CPUs, you have memory, and then you have sort of PCIe attached or NVLink attached devices, right? And typically what we think about, the host is you have CPU and memory, has an application. The application really treats this accelerator as a slave, right? There's a master-slave relationship, right? And therefore, the memory hierarchy is top-down. You've got CPU, you've got L1 cache, L2 cache, last level, and then you've got DDR, and then storage, right? You've got this hierarchy. What we're actually seeing now is that these accelerators are actually pointing upwards now. They have their own memory, they have their own caches. They can actually talk to memory now, and they actually can talk to storage. And so we have this phenomena, sort of like the inversion of the memory hierarchy. You actually have two hierarchies that are pointing against each other, which is very interesting. So keep that picture in mind. The second thing that you'll see is that over time, the relationship between the host and the coprocessor is becoming much more married, right? So back in the day in pre-CUDA 4.0, you saw the host CPUs. The host had its own memory, had its own memory address space, and the GPU had its own memory and its own address space. And things were explicit. If I want to copy something, there was an API that says, copy from this host pointer to this device pointer of this size, go, right? Things were very explicit. Then the industry changed to say, okay, well, that's too cumbersome for the programmer. We're going to have the same address space. So there's no such thing as a host pointer or device pointer. Pointer is a pointer, right? So that introduced unified memory addressing. And then the industry said, okay, well, even that's too cumbersome. Why do I even have to do a memory copy? I'm going to introduce managed memory. So as long as you have the special allocation, this allocation is now visible by the device and the host, seamlessly, without any explicit copies. Very interesting. And then in CUDA 8, they introduced truly unified memory, which is like you can just do a malloc, allocate memory, and hand that pointer to the device, and the device can actually grab that. And that's very interesting because typically in I/O, whenever you have any I/O device, whether it's networking or GPUs or storage, the memory that you want to have visible by the device has to be pinned, In this case, it's not. The device is actually grabbing memory from a virtual address space of an application. That's profound. That's really profound. And so, and in CUDA 10, what's happened is that since you have this flexibility, the GPU can actually run an entire program by itself. So it's not the GPU being the slave anymore. It can, in some cases, be the master. It's actually running a good portion of the application by itself. And so this is what I call, the inversion of compute. That now if you piece these two things together, the future is all these accelerators that will talk to each other through memory, and they actually can run a large portion of the application by themselves. So the world is kind of changing to de-emphasize CPU memory and more of these heterogeneous devices. And that's a very, very interesting future. And the last point is that, this sort of new architectures force us to create new development tools, new performance tools to really analyze where the bottlenecks are, how do we optimize our infrastructure, et cetera. And so this is part of what we've developed, and I think over time we'll be exposing some of these capabilities through vSphere.